This is a MOSFET. Through it we can use a very small voltage to control a current of over 100 amps, which is enough to drive a new energy vehicle. How does it achieve this? To understand how a MOSFET works, we first need to look at the great invention called the p-n junction. A p-n junction is divided into a p region and an n region, and both are made of the same material, a semiconductor. Common semiconductors include silicon. Zooming in, it is made of individual silicon atoms, each with 4 outer electrons, forming a stable octet with 4 neighboring silicon atoms. In this structure, electrons find it difficult to move, so the conductivity of the semiconductor is not very strong. At this point, if we add pentavalent phosphorus atoms to the semiconductor, each with 5 outer electrons, it breaks the original stable 8-electron structure, leaving an extra electron. These extra electrons can move freely since electrons are negatively charged. Negative in English, this region is called the n region. Conversely, if we add trivalent boron atoms to the semiconductor, the original 8-electron structure becomes 7 electrons. The missing electrons form holes which are positively charged. Positive in English is positive, so this region is called the p region. At this point, what happens if we connect the p region and n region together? Because the electron concentration is high in the n region, electrons will diffuse into the p region, just like water naturally flowing between two connected tanks with different water levels until balanced. Electrons entering the p region make the area near the boundary negatively charged, while the n region becomes positively charged due to the loss of electrons. The positive and negative charges on either side create an electric field, which slows down the diffusion process, that is, the movement of electrons. As diffusion continues, the electric field strengthens, further hindering electron diffusion. Eventually, a dynamic equilibrium is reached. In this state, the middle region is approximately static, with electrons no longer moving, forming the depletion layer. If a reverse voltage is applied across the junction, it strengthens the electric field, increasing the obstruction to electrons, and the current cannot flow. If a forward voltage is applied, it counteracts the existing electric field. When the applied voltage is high enough, it completely cancels the field's restraint. Electrons begin to circulate through the circuit, forming current. This forward conduction and reverse blocking give us the first semiconductor device, the diode. Now let's look at the internal structure of a MOSFET. It becomes much easier to understand. A MOSFET has 2 n regions and 1 p region. Note that the p region is not all holes. It contains a small number of electrons as well. The n and p regions are covered by an insulating layer and a metal conductive layer. 2 electrodes are connected to the n region, the source and drain. The gate is connected to the metal conductive layer. Once packaged, it looks like this. Earlier we mentioned that the n and p regions form a p-n junction, creating a diode. So if we apply a voltage between the gate and drain, no current will flow because the diode blocks it. What happens if we also connect the gate to the positive terminal of the power supply? Zooming in on the gate, unlike charges attract and like charges repel. The negative charges in the metal conductive layer are pulled toward the upper edge by the positive voltage, while positive charges are repelled to the lower edge. Back in the MOSFET, we can see the positive charges have accumulated at the lower edge. At this point, due to attraction and repulsion, the small number of electrons in the p region are drawn upward by the positive charges, forming an inversion layer. The inversion layer behaves like an n region and is filled with electrons. Therefore, the p-n junction no longer exists. Current is no longer blocked and flows freely. This is the working principle of a MOSFET. Finally, a small question: if the voltage keeps increasing, how will the current change?